So it's been my extreme pleasure to work with Charlotte this summer. We've had a very productive summer, and we've managed to work very different time zones. Charlotte has spent predominantly her time predominantly in Japan, so we've been doing morning, evening discussions. Charlotte's been a real go-getter. She's been using her skills in programming, using her skills in mathematics. And I think you'll find it very interesting, the analysis of some impact spectra that she's been looking at. So, Charlotte, take it away.
Thank you. I did a pre-recorded video because it is very, very early in the morning my time, so I don't trust myself to do a really good presentation right now. So I guess I will share my screen.
Charlotte, I'm not sure if you shared with sound when you shared your screen.
Got it. Okay, I haven't used Zoom in way too long.
In the bottom left, there should be a little.
Yes. Yes. Okay, there we go. I think that should work.
Cool.
Hello. My project was about the UV visible spectral analysis of impact samples. My mentor was Dr. Deborah Demi. I guess I will start. So introduction. So we examined samples that were impacted at the Johnson Space Center using their light gas gun facility, and this is light in the not very heavy sense. Then we measured the reflectance at the UV to visible wavelengths. So this is the 0.2 to 0.9 range of wavelengths. These samples are of basalt, gabbro, and serpentine, and we are looking at different grain sizes within these rock types to better understand the reflected light patterns of these impacted rocks. And I'm particularly looking more at grain size for this internship. So here's some examples of what they look like. This is the numbers next to the serpentine categorization are the size fraction that they are. So this is 63, the smallest, then 104 to 63, 481 to 104, and then 481, which is the biggest. And visually, the basalt, gabbro, and serpentine all look pretty similar. So first, the measurements overview. So what I'm doing is examining the overall graphs. This is an example of a basalt one. They're all pretty similarly shaped to this. So we're looking at the slopes and then the bands, which I will expand on later. So we're looking at the position, depth, and area of the bands. And this sample graph here is the same as this example sample. We are comparing slopes and bands for the UV versus visible ranges of light for this internship. So more on slopes. So these are approximated linear regressions. The basalt, we're looking at wavelengths 0.26 to 0.43, and then 0.4 to 0.8, so it's UV invisible. And then we're looking for the R-square value, which is how close the data actually maps to the regression line I found. And for this, I wrote a program in C++ to pull and process all of the data sets pretty quickly because there were 250 data sets. And so here's a small section of the output just to kind of see what it looks like with 6 of the samples. So here's more on bands. So these are these areas of the graph that kind of have these divots. So we're looking at for basalt, it's 0.22 to 0.32, and then 0.5 to 0.58, and these ranges are different for the different sample types or the different rock types we're looking at. Also, R-square value, find the lowest point, and then the X value of the lowest point will be the band position, the Y minus, or the 1 minus the Y value of the lowest point will be the band depth, and then find the band area using the integral of the regression. And so I expanded on the C++ program because, again, it would take quite a lot of time to get through. The 1 minus y for the band depth is applicable because it's normalized, and so the highest points will always be at 1. You see more here. To normalize the data, we take the band that we're looking at, and then I find the first point and the last point, and then there's a line between those points. And then to normalize it, I take every point that is of the data set and divide it by the corresponding point on the line for normalization, and then we get this normalized version of the band, which helps us compare the different samples to each other, because then the first and last point are always at 1. So to approximate the polynomial regression, I take measurements of the data set, which is using these like summations, and then find the coefficients of the regression polynomial using a bunch of like really, really long algebraic formulas. One of them was like, I think they ended up being like 250,000 characters of algebra, which was kind of insane. The program computes these approximations by taking measurements of the data set and using those through a series of these algebraic formulas to find the coefficients of the polynomial. And to be honest, I'm not entirely sure how it works, but I had to learn a bit of linear algebra to figure out how to even start finding these coefficients. Yeah. And then here's one of the data sets, what it looks like with the regression lines. You can see it's pretty, I guess it makes sense as a regression line. So then for the band position, band depth, like we just find the lowest point and yeah, the x value and then the 1 minus y value. For the band area, it's the integral under, or I guess it's over the curve between the y equals 1 for the normalized band and the regression approximation. Comparing measurements. So I'm mainly comparing the same measurements within a given sample. For example, comparing basalt UV slopes to basalt visible slopes or gabbro UV band area to gabbro visible band area. I'm also comparing each measurement against that sample's reflectance at the wavelength 0.6, and that's because it's relatively quiet at that area for most of the graphs. So it won't vary too much based on just the overall general trajectory of the graph. And then the measurement comparison graphs are separated by sample set, so we can compare the sample sets as well. So here's some examples of measurement comparisons. These are some basalt UV slopes versus basalt visible slopes. As you can see for the basalt 2357, there's no variation in the UV slope, but there is, it seems like a little bit of a grain size dependence in the visible slope, and you can see the size fractions here. It's not really a trend. And then there's not really a trend for the 2359, and then the Gabbro UV band areas doesn't have distinctions. So patterns I noticed. For the basalt, when there is a visible distinction between size fractions, the larger size tends to be in between the small and medium size fractions. You see this is 63, this is 481, 104, and then this is the biggest one, which is 481. And then basalt more often has these clumps that kind of have this non-trend but still separated than the other rock types. And then the small size fraction of the red here tends to be the most tightly clumped. For part 2 of basalt, in the visible, all samples of the 481-104 size fraction of the 2357 sample set and the 481 size fraction of the 2359 sample set had no band. As you can see here, they just kind of look like noisy lines. And then these ones are still kind of noisy lines, but they're a lot more clearly bands than these ones. For the Gabbro, most of the Gabbro comparisons had no clear correlations, although for some reason the 2510 had very clear distinctions in the linear slope. You can see here, and then these are just kind of, these don't really have clear distinctions. Gabbro's 2510 reflection at the wavelength 0.6 clump size fractions, as you can see here, but you can't really look at a trend for this because there's only 2 different size fractions, because this one is like it's not really size fraction because it's the melt. The serpentine, the small size fraction tends to be the most tightly clumped, similar to basalt, and then otherwise no really discernible patterns. Here's just a trend, is that the UV bands tend to be much like clearer than the visible ones. Like they're super noisy, these aren't. And then again, the small size fraction tends to be most clearly clumped. So here's some general conclusions. There's no overarching clear correlation. It seems like this is kind of a null result. And then sometimes sometimes a grain size would very consistently exhibit a particular reflections pattern or lack thereof, but only within one sample. So you can see here, like the biggest size for basalt's 2359 band depth was like very consistently didn't have a band. The negative implies that it doesn't have a band because it's weird to have the depth be above the normalization. But then the 2361 sample set, the band depth, it does pretty consistently have a band. So like within the sample set, they tend to have more patterns than overall. future directions, I could possibly do the same measurements and comparisons for the infrared reflectance because we have that data. Or if there is anything like particularly interesting about these, individually examine the samples under an electron microscope. Acknowledgements and acknowledgements. So I would like to acknowledge Dr. Deming. Thank you for being a great mentor and the N3 program. Some notable resources I used, people on Stack Exchange, very useful. I used words and buttons on dot online for the polynomial approximation technique, and decode, which took me forever to find, for the Gaussian elimination calculator. And I found it right at the last minute before like diving headfirst into trying to learn Python and a lot more linear algebra to try to code it on my own. Also, thank you to my friend who somehow agreed to get on call with me, very delirious after an all-nighter, and also at 2 a.m. his time to teach me all of basic linear algebra. I very much appreciate that. Yeah, thank you. Any questions?
Well, first, let's give a round of applause to Charlotte for pretty large amount of analysis. It's really interesting. I wish I understood more about rocks, but at least I got a little bit of a glimmer from it. What do you expect to find if you get to look at the infrared spectra?
I don't know. I guess I don't know. I would expect it to be, I guess, somewhat similar, but because I haven't looked at any of it yet, I am not entirely sure what I would see.
Well, I have no clue, so we're even on that. But maybe Dr. Ming has some ideas.
Well, we would look for very similar things to what we looked at in the UV invisible. Do the bands shift, and do they shift consistently? Charlotte may think she got a null result in the fact that we don't see any correlations with grain size, but what it means is that the variations we see are due to the impact process. And that's what we were hoping to pull out. Are we seeing spectral changes due to impact? So we've ruled out that, hey, it's a grain size thing. Now we can start looking at, okay, what has this process done to these minerals? So it's far from a null result. I think she's done a fantastic job.
I totally agree. Do we have any other questions?
All right, I think we can move on to our second presenter then.